There is a place in the universe where something the size of our entire galaxy exists, and yet is almost completely invisible. Not dim, not faint, not obscured by dust or distance or the limitations of our instruments. Invisible in a way that goes deeper than optics, deeper than light, deeper than anything our senses were ever built to perceive. A structure containing the gravitational mass of 1 trillion suns, suspended in space like an enormous ghost, holding its shape across billions of years without a single star to justify its presence. A galaxy that should not exist, and yet does right there, immovable and vast, in a corner of the sky that most people have never looked at, and most telescopes once ignored entirely. Its name is Dragonfly 44, and when astronomers first resolved its shape in 2016, using a telescope built not from cutting-edge optics, but from an array of telephoto lenses borrowed from commercial cameras, what they found shattered one of the quieter assumptions of modern cosmology, that we basically understood what a galaxy was. You think you know what a galaxy is. You've seen the images, swirling arms of light, dense cores blazing with ancient suns, curtains of gas and dust catching starlight like fog lit from within. The Milky Way, Andromeda, the Whirlpool, the Sombrero, each a cathedral of luminous matter, each containing hundreds of billions of stars arranged by gravity into something almost architectural. You've absorbed the idea that a galaxy is, fundamentally, a visible thing, a collection of light, a structure you can point to and say, there it is. Dragonfly 44 is not that. Dragonfly 44 is roughly the same size as the Milky Way. In volume, in total gravitational mass, in the space it occupies in the Coma cluster some 320 million light-years from Earth, it is comparable to the galaxy you live in. And yet it contains fewer than 1/100th of the stars our galaxy holds. Not 1/10th, not 1/5, 1/100th. Where the Milky Way blazes with somewhere between 100 and 400 billion stars, Dragonfly 44 holds perhaps 1 billion, scattered and dim and diffuse, like embers in a field where a bonfire should be burning. The rest of the structure, the vast overwhelming bulk of it, is made of something else entirely, something we cannot see, something we cannot touch, something we have never, not once, not in any laboratory, not in any detector built anywhere on this planet, directly confirmed. The something is dark matter, and Dragonfly 44 is approximately 99.99% composed of it. Let that settle for a moment. Not as a statistic, as a reality. The object you are now contemplating, an object larger than the galaxy that contains every star you can see from Earth on the clearest night of your life, is, for all practical purposes, made entirely of a substance that physics cannot fully describe, that no instrument has ever touched, and that exists in our models only because the universe refuses to make sense without it. Dragonfly 44 is not mostly dark matter the way a planet is mostly rock with some iron mixed in. It is dark matter the way a shadow is darkness, constitutively, essentially, almost exclusively. And the moment you understand what that means, the question changes. It stops being a question about one unusual galaxy in a distant cluster. It becomes a question about what the universe is actually made of, how much of reality has been hiding from us in plain sight, and whether everything we thought we understood about the cosmos, about structure and formation and the long, slow birth of light out of darkness, was built on a foundation far less solid than we assumed. If you find yourself drawn to questions like this one, to the edges of what we know, to the places where knowledge fades into genuine mystery, stay with this. Leave a like, subscribe if you haven't already, and let's keep going together, because what follows only gets stranger. The story of Dragonfly 44 begins, in a sense, not with the galaxy itself, but with the telescope that found it. In 2013, a team of astronomers led by Peter Van Dokkum at Yale University constructed an instrument unlike anything in the arsenal of conventional observatories. They called it the Dragonfly Telephoto Array. It was made of off-the-shelf Canon telephoto lenses, the kind of equipment a wildlife photographer might use. arranged in a cluster and linked together to form a single imaging system with unusually low optical scattering. The design wasn't glamorous. It didn't look like the towering instruments of Mauna Kea or the sweeping mirror of the Hubble. It looked, frankly, like something assembled in a garage. But it was built for a specific purpose: to see things that other telescopes were systematically missing. When light scatters inside a traditional telescope's optical system, it washes out the faint, diffuse structures that live at the edges of visibility. Objects so low in surface brightness that conventional instruments simply cannot pull them out of the background glow of the sky. Dragonfly was designed to suppress that scatter, to see the dim and the ghostly, to find what the bright sky bias of astronomy had been overlooking for decades. And what it found, when it turned toward the Coma cluster, was a population of objects no one had expected in those numbers: ultra-diffuse galaxies. Galaxies that were large in size but almost empty of stars. Galaxies that existed at the threshold of visibility, neither here nor fully there. Present as gravitational fact, but nearly absent as luminous reality. In the Coma cluster alone, the Dragonfly team eventually cataloged hundreds of them, and among those hundreds, one stood out as something beyond unusual: Dragonfly 44. When Van Dockum and his colleagues measured its velocity dispersion, essentially how fast the stars inside it were moving relative to each other, they got a number that made no immediate sense. The stars were moving too fast, far too fast to be held in their orbits by the gravity generated by 1 billion visible stars. If you calculated the mass that would be required to keep those stars from flying off into space, you arrived at a figure roughly equivalent to the mass of the entire Milky Way. But the stars visible in Dragonfly 44 could only account for a tiny fraction of that mass. The rest had to come from somewhere else, from something invisible. The calculation was straightforward, in the cold language of orbital mechanics and gravitational dynamics. The implications were not, because what the numbers were saying, in effect, was that Dragonfly 44 was a galaxy almost entirely composed of matter that interacted with its stellar population only through gravity, that shaped the orbits of those scattered stars, held the entire diffuse structure together across billions of years, and yet contributed nothing to the galaxy's light, nothing to its warmth, nothing to any signal that any instrument designed to capture electromagnetic radiation could detect. The galaxy was there, but most of what made it a galaxy, most of what held it together, most of what gave it mass, most of what made it real in any physical sense, was completely, profoundly, stubbornly invisible. And here is where the story shifts from the strange to the genuinely unsettling. Because Dragonfly 44 did not represent the discovery of dark matter. Dark matter had been inferred since the 1930s, when the Swiss astronomer Fritz Zwicky first noticed that galaxies in clusters were moving too fast to be held together by visible mass alone. It had been mapped indirectly through gravitational lensing, traced in the large-scale structure of the cosmic web, embedded in the standard model of cosmology as a fundamental ingredient of the universe. Roughly 27% of the total energy mass content of the cosmos is thought to be dark matter. You are surrounded by it right now as you read this. It passes through you, through the earth, through the sun, through the walls of every laboratory ever built, as if none of those things existed. What Dragonfly 44 represented was something different, something almost more disturbing than the initial discovery. It was proof that a galaxy could be built almost entirely from this invisible substance. That the visible universe, the stars, the gas, the dust, everything that has ever reflected or emitted a single photon that a human eye or human instrument has ever recorded, could be so thoroughly subordinated to the dark that it became, in effect, decorative, incidental, almost irrelevant. The light was not the galaxy. The dark was. And if that is true for Dragonfly 44, the question that the universe immediately places before you is one you cannot easily set aside. How many other things are like it? How much of what we have never seen is real? How much of the cosmos is made of something we have never touched, never measured, never even come close to naming correctly? The answer, it turns out, is almost everything. To understand what Dragonfly 44 truly represents, not as a data point but as an experience, as something that can land in the body with the weight it deserves, you need to first build a sense of scale. Not the abstract numerical kind of scale that appears in textbooks and dissolves almost immediately from memory. The visceral kind, the kind that makes your perception of the universe physically shift. Start here. Step outside on a clear night and look up. On a good night, far from city lights, you can see roughly 5,000 stars with the naked eye. 5,000 points of light, scattered across the dome of the sky, some steady and pale, some flickering at the horizon, a few bright enough to cast faint shadows. That entire collection, every star you can see with your own eyes, unaided from anywhere on Earth, belongs to the Milky Way. And those 5,000 visible stars represent something close to nothing, a vanishingly small sample of the 200 to 400 billion stars that populate our galaxy in total. Now hold that number. 200 billion stars minimum. Each one a sun, many of them larger and hotter than ours, most of them circled by planets. The Milky Way is, by any human measure, an incomprehensible abundance of light and matter and nuclear fire, stretched across a disk roughly 100,000 light-years in diameter. If you could travel at the speed of light, 300,000 kilometers per second, fast enough to circle Earth 7 times in a single heartbeat, it would still take you 100,000 years to cross it from one edge to the other. That is the Milky Way. That is the object we use as our intuitive baseline for what a galaxy is, because it is the one we live inside. Now hold the Milky Way in your mind. All of it. The blazing central bulge, the sweeping spiral arms, the halo of ancient globular clusters hovering above and below the disk, the thin stream of the galactic plane you see as a smear of light on dark summer nights. Hold that entire structure, all 200 billion stars of it, all 100,000 light-years of it, and place it in space. Now place Dragonfly 44 next to it. Same diameter, same volume, same gravitational mass, according to the orbital dynamics of its stars. You have 2 objects of equivalent size sitting side by side in space. One of them is our galaxy, blazing, dense, baroque with stars, its spiral arms etched in blue and gold and red, its core a knot of ancient light. The other is Dragonfly 44, diffuse, pale, nearly featureless, its surface brightness so low that a sky slightly brighter than perfect darkness would make it invisible entirely. Fewer than 1 billion stars in a space designed to hold hundreds of billions. The rest of the structure, the gravitational scaffold that holds those stars in their orbits, the mass that makes the whole thing cohere across cosmic time, is not there. Or rather, it is there, but it is something else. Imagine building a city, a real city, Manhattan perhaps, or São Paulo, or Shanghai. You design the streets, lay the foundations, run the infrastructure, build the underground systems that will move water and power and people. You construct the entire invisible skeleton of the city, the drainage networks, the transit tunnels, the electrical grids, the communication cables, and then you build the buildings, but not all of them. You build perhaps 1 building for every 100 that the skeleton was designed to support. 1 tower where 100 should stand. 1 neighborhood of light in a grid prepared for a metropolis. From a distance you would see almost nothing, a handful of lit windows in an enormous darkness. But the streets would be there. The infrastructure would be real. The capacity of the city, its gravitational presence in a sense, would be that of a full metropolis. It just wouldn't look like one. That is Dragonfly 44. A galaxy built for 100 billion stars, holding barely 1 billion. An infrastructure of dark matter spanning 100,000 light-years, populated by a scattering of dim, ancient suns, too sparse to give the structure the appearance it deserves. A city of ghost streets and dark skyscrapers, with just enough light to confirm that something is there, and just little enough to deny you any clear view of what. But before you can feel the full weight of what Dragonfly 44 implies, you need to hold something else, what dark matter is, or more precisely, what it is not. It is not a gas cloud too cold to emit light. Cold gas clouds have been detected. They absorb and emit at radio wavelengths that our instruments can see. It is not a population of black holes hiding between the stars, although black holes have been considered and, for dark matter in its total quantity, largely ruled out. It is not failed stars, brown dwarfs, dim and cool and faint, because the numbers simply don't work. It is not antimatter, not a mirror universe leaking gravity into ours, not a gravitational illusion generated by our misunderstanding of how gravity behaves at large scales, though that last possibility has a respectable minority of physicists still advocating for it. Dark matter, as currently understood in the standard cosmological model, is something that has never been assigned a definitive particle identity. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force at all, which means it is invisible not merely because it's too dim or too cold, but because it has no relationship with photons whatsoever. Light passes through dark matter as if dark matter simply isn't there. The two substances occupy the same space without acknowledging each other. To a photon, dark matter is less than air. It is nothing. And yet to gravity, dark matter is entirely real. It bends space-time. It attracts other matter. It pools and clumps and forms enormous halos around galaxies, providing the scaffolding without which the visible universe, stars, gas, planets, would never have coalesced into anything recognizable. Think about what that means for a moment. The substance that makes up 27% of all the energy and mass in the observable universe, the ingredient without which no galaxy, including the one you live in, would have formed, cannot be seen, touched, felt, or directly measured by any instrument humanity has ever built. It is inferred, implied, known only through its effects, the way you can know that a wind is blowing, not because you can see the air move, but because you see what the air does to the leaves. We live inside the consequence of dark matter. Every star in the night sky, every planet in every solar system, every galaxy in every cluster exists because dark matter was there first, pulling ordinary matter together into concentrations dense enough to collapse under their own gravity and ignite. Dark matter did not merely shape the universe. Dark matter made the universe possible. And in Dragonfly 44, this invisible architect is present in almost pure form, undiluted by the ordinary matter that in most galaxies gives the dark a luminous mask to wear. This is why Dragonfly 44 is not simply an astronomical curiosity. It is not merely a weird edge case, a statistical outlier to be noted and moved past. It is a place where the thing that underlies all cosmic structure is exposed almost without cover. A place where the skeleton of the universe protrudes through the skin. A place where, if we could only find the right instrument, the right frequency, the right window into physics we haven't yet built, we would be looking directly at the dominant substance of the cosmos, naked and unobscured, and we still cannot see it. That fact, that we are staring at an object 99.99% composed of something we cannot identify, in a universe 27% composed of the same unknown substance, with no detection to our name after nearly a century of searching, that fact is not a failure of science. Science has mapped the shadow of dark matter across the entire sky. Science has measured its effects to extraordinary precision. But something about its fundamental nature remains, at this moment, completely beyond us. Which raises the question, what exactly are we missing? What would it mean to finally know what dark matter is? And what would it say about reality, about the nature of matter, the behavior of forces, the architecture of the cosmos? If the most abundant substance in the universe turned out to be something that existing physics never predicted, the answers, as always, begin with the question itself. And the question, standing at the edge of what Dragonfly 44 reveals, is about to get much larger. The Coma Cluster is not a gentle neighborhood. It is one of the densest concentrations of galaxies in the observable universe, a gravitational metropolis containing over 1,000 individual galaxies, compressed into a region roughly 20 million light-years across, all of them bound together by the mutual pull of their combined mass. all of them moving through each other's gravitational fields in slow, majestic, catastrophic arcs that will, over billions of years, result in collisions, mergers, disruptions, and the slow consumption of smaller structures by larger ones. The coma cluster is where galaxies go to interact, where the ordinary rules of isolated evolution are overwritten by proximity, tidal forces, and the brutal arithmetic of gravitational dynamics. It is also, not coincidentally, where ultra-diffuse galaxies like Dragonfly 44 seem to cluster most densely, and that is not a coincidence you can ignore. Because when you look at where ultra-diffuse galaxies, those enormous, nearly empty structures with their absurdly low star counts and their overwhelming dark matter fractions, tend to appear in largest numbers, you find them preferentially in the most extreme environments. Dense clusters, gravitationally violent regions, places where the ambient tidal forces are strong enough to strip gas from galaxies, disrupt their star-forming processes, and fundamentally alter the course of their evolution, which immediately suggests a story, or at least the outline of one. Maybe these galaxies were not always like this. Maybe they didn't begin their lives as dark, diffuse, nearly starless structures. Maybe something happened to them. Maybe the environment made them what they are. This is the first major fracture in the seemingly simple narrative of Dragonfly 44, because there are, broadly speaking, two competing explanations for why a galaxy might end up with 99.99% dark matter and almost no stars, and they lead in radically different directions. The first is an external story. A galaxy that was once more ordinary, more luminous, more star-rich, was stripped of its gas and its outer stars by tidal forces, gravitational interactions with the enormous mass of the cluster itself, or with other galaxies passing nearby, leaving behind only the deeply embedded dark matter halo that tidal forces cannot so easily peel away. The second is an internal story. A galaxy that formed differently from the very beginning, that emerged from the early universe already dominated by dark matter, that never had the gas density or the conditions to form stars in significant numbers. These two stories are not merely academically different. They imply different things about the universe itself. If the first story is true, the stripping hypothesis, then ultra-diffuse galaxies are victims of environment, cautionary tales about what clusters do to their members over cosmic time. Ordinary galaxies disrupted and impoverished. If the second story is true, the primordial formation hypothesis, then ultra-diffuse galaxies represent a genuinely different mode of galaxy formation, a path through the early universe that leads not to blazing spirals or elliptical giants, but to pale, dark-dominated structures that might always have been this way, that were never anything other than what we see. The disturbing thing is that both explanations might be correct for different objects. The universe does not feel obligated to give us one clean answer. But set aside for a moment the question of origin. Set aside how Dragonfly 44 came to be, and consider instead something that has been sitting quietly in the background of everything said so far, waiting for the right moment to announce itself. You have been told that dark matter makes up approximately 27% of the universe's total energy mass content. You have been told that ordinary matter, everything you can see, touch, eat, breathe, build, measure, or destroy, makes up approximately 5%. You have perhaps encountered these numbers before, in a science article, a documentary, a classroom. Perhaps you accepted them as interesting, registered them as surprising, and moved on. But now, with Dragonfly 44 as your reference point, try to sit with them differently. 5%. Everything that has ever emitted or reflected light in the history of the cosmos. Every star, every galaxy, every nebula, every planet, every moon, every asteroid, every comet, every atom of gas floating in intergalactic space, every molecule in every ocean on every world that might exist in the 93 billion light-year span of the observable universe, adds up to 5% of what's out there. The rest is dark. Not dark as in unlit, dark as in fundamentally different. Dark matter at 27%, and then something even more dominant and even more mysterious, dark energy, accounting for the remaining 68%. The universe is, by composition, 95% things we cannot directly detect. You are not living in a cosmos of light and matter. You are living in a cosmos where light and matter are the exception, where the blazing, intricate, luminous universe that astronomy has spent 4 centuries mapping and cataloging represents a thin film of the ordinary floating on an ocean of the unknown. Every telescope ever built, every observatory ever founded, every photon ever collected and analyzed and argued over has been studying 5% of what exists. The rest has been there all along, shaping everything, governing the structure of the entire universe, and remaining completely opaque to every instrument we have designed. Dragonfly 44 makes this abstract fact into something you can almost see. It is the universe's composition made visible by extreme example. It is what you get when the 5% is reduced to a rounding error and the 27% is allowed to dominate without disguise. It is a galaxy that does not hide what the universe actually is. Most galaxies wear their dark matter beneath a bright exterior of stars and gas. Dragonfly 44 wears almost nothing else. Its dark matter halo is its body, its substance, its reality. The stars scattered through it are almost incidental, witnesses to a gravitational architecture they didn't build and couldn't sustain on their own. Now expand the scale once more, because Dragonfly 44 is not alone. Since the Dragonfly telephoto array began its survey of the sky, hundreds of ultra-diffuse galaxies have been cataloged in the Coma cluster alone. As observational techniques have improved and as surveys have expanded to other galaxy clusters, Virgo, Fornax, Hydra, Perseus, the number has grown into the thousands. The universe appears to be full of these objects. They were invisible to previous surveys, not because they don't exist, but because the tools we had were not designed to see them. The bias of our instruments had hidden them from us for decades. We had been looking at the universe through a filter tuned only to the luminous, and the dark had simply slipped through. What this means, and the implications accumulate faster than they can be absorbed, is that our census of the universe has been systematically incomplete, not slightly incomplete, not missing a few edge cases. Incomplete in a way that changes the character of what a galaxy cluster is, what galaxy formation means, and how the cosmos distributes its dark matter across the structures it creates. If thousands of ultra-diffuse galaxies exist in every major cluster, and if their dark matter content is anywhere near what Dragonfly 44's measurements suggest, then the total dark matter inventory of these clusters is substantially larger than previous models assumed. The dark web of the universe is denser than we thought, more intricate, more populated with structures that carry mass without carrying light. And here is where the vertigo begins in earnest. Because the further you push into this territory, the more you attempt to account for all the dark matter in all the clusters, all the ultra-diffuse galaxies in all the surveys, all the gravitational signals that don't quite match the visible mass. The more you begin to suspect that the visible universe is not merely surrounded by the dark. It is threaded through by it, woven into it, dependent on it at every scale, from the formation of the first structures after the Big Bang, to the stability of the galaxy you live in, to the orbit of every star and every arm of the Milky Way. Dark matter is not something that exists out there, in extreme objects like Dragonfly 44, in the exotic fringes of the cosmos. It is here. It interpenetrates the room you sit in. It flows through your body at this moment, hundreds of billions of particles per second passing through every square centimeter of you without leaving a mark, without triggering a single atom in your flesh, without any interaction except the faintest imaginable gravitational whisper that no instrument on Earth has been sensitive enough to catch. You are not merely studying dark matter when you study Dragonfly 44. You are, in a very literal sense, studying the invisible ocean in which you swim. And the ocean, it turns out, is far deeper than anyone thought. In 1933, a man named Fritz Zwicky stood in front of his colleagues at a meeting of the American Physical Society and told them, in the blunt and combative style that would define his entire career, that something was wrong with the Coma cluster. Zwicky had been measuring the velocities of galaxies within the cluster, the speed at which individual galaxies moved relative to each other as they orbited the cluster's common center of mass. and the numbers he found were impossible. Not unexpected, not slightly off. Impossible. The galaxies were moving so fast that, if the only mass holding the cluster together were the mass visible in its constituent galaxies, the cluster could not exist. The galaxies would have long since flung themselves apart, scattered into the void, leaving nothing behind. But the cluster was there, had been there for billions of years, was, by all evidence, stable, which meant there had to be more mass than was visible, a lot more mass. Zwicky estimated that the Coma cluster contained at least 400 times more mass than could be accounted for by its luminous content. He called it dunkle materie, dark matter. Nobody paid much attention. The idea was too radical, the evidence too indirect, and Zwicky himself too abrasive for comfortable collaboration. The concept sat at the margins of physics for decades, occasionally surfacing in anomalous measurements, occasionally generating a paper, never quite commanding the consensus it needed to transform from curiosity into cornerstone. Then, in the 1970s, Vera Rubin changed everything. Rubin was studying the rotation curves of spiral galaxies, graphs showing how fast stars at different distances from the galactic center orbit around it. According to Newtonian mechanics and the distribution of visible mass, the pattern should have been predictable. Stars near the center orbit fast, stars at the outer edges orbit slow, the curve dropping off with distance the way the planets of our solar system slow down as they move farther from the sun. This was not what Rubin found. The rotation curves of spiral galaxies were flat. Stars at the outer edges were orbiting just as fast as stars near the center, sometimes faster. The mathematics was unambiguous. Either gravity behaved differently at galactic scales than Newton and Einstein predicted, or there was a vast amount of invisible mass surrounding every spiral galaxy, a halo of something extending far beyond the visible disk, providing the gravitational pull that kept the outer stars locked in their too fast orbits. Rubin's data was clean, reproducible, and eventually impossible to dismiss. Galaxy after galaxy, the same flat rotation curves, the same implied dark matter halos, the same invisible architecture encasing every luminous structure in the universe. And with that, dark matter moved from the margins to the center. It became not a peculiarity, but a necessity, a foundational ingredient of the standard model of cosmology, something the universe required, something without which the entire architecture of structures, galaxies, clusters, the cosmic web of filaments and voids, could not have assembled itself from the near-uniform fog of the early universe into the intricate hierarchical cosmos we observe today. But here is the paradox that has been building since 1933, since Rubin's rotation curves, since every gravitational lensing map and every cosmic microwave background measurement and every simulation of large-scale structure formation that has confirmed dark matter's presence and influence. Here's the thing that keeps the physicists awake. After nearly a century of knowing that dark matter exists, we still do not know what it is. Not in the way we don't know what happened before the Big Bang, which is a question about a boundary condition beyond our observational reach, and not in the way we don't know whether there is life on Europa, which is a question of access and instrumentation. This is a different kind of not knowing. This is a not knowing that sits inside the standard model of particle physics, like a locked room in a house you otherwise know intimately. The standard model, the theoretical framework that describes every known particle and every known force except gravity, has no dark matter particle, no candidate within its own structure, no room in its taxonomy for something that has mass, gravitates, but refuses every other interaction. This means that whatever dark matter is, it is something beyond the standard model, something that current physics, for all its extraordinary precision in other domains, does not contain. The particle, or particles, or field, or whatever form dark matter takes, lies outside the framework that describes every atom in your body, every photon that has ever struck your retina, every force that has ever acted on any piece of ordinary matter anywhere in the observable universe. Dark matter is not hiding inside physics we have. It is pointing toward physics we don't. Physicists have proposed candidates, many of them, over many decades, with many variations. WIMPs, weakly interacting massive particles, were for a long time the leading hypothesis, motivated by theoretical elegance and by a coincidence called the WIMP miracle. The observation that a particle with the right mass and interaction strength to arise naturally from supersymmetric extensions of the standard model would also be produced in exactly the right abundance during the Big Bang to account for the observed dark matter density. This coincidence was so striking that it convinced a generation of physicists that WIMPs were almost certainly what dark matter was, and a generation of experiments was built to find them. The experiments found nothing, not a hint, not a statistical anomaly, not a signal buried in noise. Underground detectors filled with liquid xenon, cooled to temperatures near absolute zero, shielded from cosmic rays by kilometers of rock, capable of registering the energy deposited by a single recoiling nucleus. These instruments, among the most sensitive ever built, looked for WIMPs and found silence. The WIMP miracle began to look less like a miracle and more like a coincidence. And as the exclusion limits tightened, as the experiments ruled out larger and larger regions of the parameter space where WIMPs might hide, the theoretical community began, slowly, reluctantly, to look elsewhere. Axions became fashionable. Axions are hypothetical particles originally proposed not to explain dark matter, but to solve a different problem in quantum chromodynamics. They are extraordinarily light, extraordinarily weakly interacting, and if they exist in sufficient numbers, they could constitute dark matter. Experiments to detect them, based on the prediction that axions should occasionally convert into photons in the presence of strong magnetic fields, have been running for years. So far, no confirmed detection. Sterile neutrinos, primordial black holes, self-interacting dark matter with novel force mediators, dark sector particles that interact with ordinary matter through new forces we haven't discovered. The theoretical landscape has grown rich and complicated and increasingly unconstrained by data because the data stubbornly refuses to arrive. Every null result narrows the space of possibility. Every null result also deepens the puzzle because it means the simplest and most theoretically motivated candidates have been ruled out, and what remains are either more exotic possibilities or the most unsettling alternative of all, that dark matter doesn't exist as a particle, that gravity itself is different from what we think, that general relativity breaks down at galactic scales in ways that mimic the presence of invisible mass. Modified gravity theories, MOND, and its relativistic extensions, have their advocates. They can explain some observations remarkably well. They fail at others. They struggle with galaxy clusters, with the cosmic microwave background, with the large-scale structure of the universe. No modified gravity theory has yet managed to replace dark matter cleanly across all scales and all observations. The contest remains unresolved. This is the true abyss at the center of Dragonfly 44's story, not the strangeness of the galaxy itself, striking as it is. The abyss is this: we are living inside a universe where the dominant component of all gravitational structure is something we cannot identify, cannot detect directly, and cannot explain from first principles. We have mapped its effects with extraordinary precision. We have traced its influence from the earliest moments of the universe to the present day. We have confirmed over and over that without it the cosmos as we know it cannot exist, and we do not know what it is. Dragonfly 44 is not just an astronomical curiosity. It is the universe holding up a mirror to the deepest limitation of human knowledge. It is the cosmos saying, "Look at this. Look at this enormous, ancient, gravitationally coherent structure. Look at how it's built almost entirely from something you haven't named. Look at how much of me is like this, invisible and unknown, bearing the weight of everything you can see." And then ask yourself how much you truly understand. To understand why dark matter is so difficult to find, you need to understand something about the nature of interaction itself, about what it means, at the most fundamental level, for two things to affect each other. In the physical world, matter communicates through forces. Particles influence other particles through the exchange of force carriers, the photon for electromagnetism, gluons for the strong nuclear force, W and Z bosons for the weak nuclear force, and the graviton, still hypothetical, for gravity. Every interaction you have ever experienced in your life, every sensation of touch, every moment of warmth, every flash of light entering your eye, is the result of particles exchanging force carriers with other particles. Your hand pressing against a table is not actually solid meeting solid in any intuitive sense. It is the electromagnetic repulsion between electron clouds, billions upon billions of electrons refusing to occupy the same space, mediated by a torrent of virtual photons passing between them at unimaginable speeds. You interact with the world because you are made of electrically charged particles, and electrically charged particles communicate constantly and prolifically through photons. Your atoms broadcast their presence. They absorb and emit light. They push and pull on the atoms around them. They are, in the language of physics, coupled, locked into a constant conversation with the electromagnetic field that permeates all of space. Dark matter does not participate in this conversation. Whatever dark matter is made of, its particles, if they are particles, do not carry electric charge. They do not interact with the electromagnetic force. They do not emit photons. They do not absorb photons. They do not push or pull on electrons. They pass through ordinary matter the way a ghost passes through walls in the stories humans have always told about the invisible presences that share our world. Not because they are supernatural, but because the medium through which ordinary matter announces itself is simply not a medium that dark matter uses. This is the fundamental reason why dark matter cannot be seen. Not because it's too dim, not because it's too far away, but because the entire electromagnetic spectrum, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, is a language that dark matter does not speak. Every telescope ever built is an instrument for collecting photons, and dark matter generates no photons. It has nothing to say in the only language our instruments are designed to hear. What dark matter does speak is gravity, and gravity is extraordinary in its own way. The only force that reaches across all of space without diminishing to zero. The only force that acts on everything with mass. The only force that curves space-time itself rather than merely acting within it. But gravity is also, by far, the weakest of the known forces. The electromagnetic force between two electrons is roughly 10 to the power of 42 times stronger than the gravitational force between them. A number so large it barely registers as a number. For practical purposes, gravity between individual particles is almost unmeasurably small. It only becomes significant when enormous quantities of mass accumulate in one place, which is exactly what happens in galactic halos, where the collective gravitational pull of trillions of dark matter particles shapes the orbits of stars across thousands of light years. This is the deep irony of dark matter research. The force through which dark matter reveals itself, gravity, is the weakest force in nature. The force through which it hides, by refusing to engage with electromagnetism, is the force we are best equipped to measure. Dark matter is maximally elusive by physics. Its properties seem almost engineered for invisibility, though of course the universe engineered nothing. It is simply what it is, and what it is happens to be extraordinarily difficult to catch. So how do you search for something that will not be seen, that will not be felt, that passes through everything without leaving a mark? You build the most sensitive listening devices in human history, and you put them in the deepest, most shielded environments you can find, and you wait. You wait for the extraordinarily rare event in which a dark matter particle, passing through your detector at a speed of hundreds of kilometers per second, the typical velocity of dark matter particles in the galactic halo, a consequence of the gravitational dynamics of the Milky Way, collides not with an electron, which it ignores, but with an atomic nucleus, not through electromagnetism, which dark matter doesn't use, but through the weak nuclear force or through direct gravitational scattering, interactions so faint that detecting them requires instruments capable of measuring energy depositions of a few electron volts or less, in detectors the size of bathtubs, cooled to temperatures a fraction of a degree above absolute zero. The Lux Zeppelin detector in the Homestake mine in South Dakota, the Xenon T detector buried beneath the Gran Sasso mountain in Italy, the Pandex 4T detector in the China Jinping underground laboratory, sitting beneath 2,400 meters of solid rock to shield it from cosmic rays that would otherwise mimic the signals it's looking for. These instruments represent humanity's most serious attempts to catch dark matter in the act of doing almost nothing, to register the faintest possible whisper of an interaction between the invisible and the real. And yet the whisper so far has not come. Each experiment has improved on its predecessor's sensitivity. Each has pushed the exclusion limits further, ruled out more of the parameter space, narrowed the range of masses and interaction strengths where WIMPs could hide. And each null result, presented with meticulous care and rigorous statistical analysis, has made the WIMP hypothesis slightly less plausible, the theoretical landscape slightly more constrained, the mystery slightly deeper. There is a particular kind of scientific frustration that is different from ordinary failure. Ordinary failure means your hypothesis was wrong and you need a new one. The frustration of dark matter detection is different because the hypothesis that dark matter exists, that it gravitates, that it shaped the universe, is almost certainly correct. The evidence for dark matter's existence is overwhelming. What is failing is not the idea, but the specific proposals about what dark matter is made of. It exists. We just don't know what it's made of. And every experiment that rules out another candidate is not telling us dark matter doesn't exist. It's telling us that dark matter is stranger than we thought. There is another approach. Instead of waiting for dark matter to collide with detectors, you can try to create it. If dark matter particles exist with masses and interaction strengths in the range accessible to particle accelerators, then collisions at high enough energies should occasionally produce them. The Large Hadron Collider at CERN, capable of accelerating protons to 99.991% of the speed of light and smashing them together with energies of 13.6 trillion electron volts, has been searching for signatures of dark matter production since it began operations. The signature would be distinctive, a collision event in which less energy and momentum appear in the detector than went into the collision, because some of it walked away invisibly, carried off by a dark matter particle that the detector cannot see. So far, no confirmed dark matter production at the LHC. The accelerator has discovered extraordinary things. The Higgs boson in 2012, a cornerstone of the Standard Model's mechanism for giving particles mass. It has measured the properties of known particles with breathtaking precision. It has probed energy scales that were beyond reach a generation ago. But dark matter, if it exists in the mass range the LHC can probe, has not shown itself, which either means dark matter is heavier than the LHC can reach, or lighter than its detector thresholds, or interacts so weakly that even the LHC's prodigious collision rate isn't enough to produce detectable quantities, or is something so radically different from any particle the Standard Model prepared us for, that the entire strategy of looking for it in accelerator collisions was misconceived. And then there is indirect detection. If dark matter particles are their own antiparticles, a theoretical possibility for certain candidates, they should, when two of them collide in regions of high dark matter density, annihilate each other and produce Standard Model particles, gamma rays, positrons, antiprotons, neutrinos. These signals should be detectable by space-based observatories like the Fermi Gamma Ray Space Telescope, which has been scanning the sky for anomalous gamma ray emissions from the galactic center, from dwarf galaxies, from galaxy clusters for over 15 years. The galactic center shows excess gamma rays. It does. But whether that excess is from dark matter annihilation or from unresolved populations of pulsars and other conventional sources is a debate that has not been resolved. The signal is there. The interpretation is not settled. Every candidate explanation has advocates and objections. The universe, characteristically, is not making this easy. What all of these approaches share, direct detection, collider production, indirect detection, is that they all depend on dark matter interacting with ordinary matter through something other than gravity. They all require dark matter to have at least some faint coupling to the Standard Model, some thread of connection, however thin, through which the two sectors can communicate. If dark matter interacts only gravitationally, if gravity is literally the only force it couples to, then all of these strategies fail. Not because the experiments are poorly designed, but because the physics simply doesn't permit the kind of signal they're looking for. A purely gravitational dark matter candidate would be, for all practical purposes, undetectable by any instrument we know how to build. We would know it existed through its gravitational effects on every scale from galactic rotation curves to the cosmic microwave background, and we would have no way of ever learning what it was made of. This is the edge of the abyss, not a metaphorical edge, a real epistemic boundary where the tools of physics, designed to catch particles through their interactions, collide with the possibility that the most abundant material in the universe simply doesn't interact enough to be caught. Dragonfly 44 floats in that abyss, made of something that holds it together without being seen, without being touched, without registering on a single detector in any underground laboratory on Earth. Enormous and ancient and patient, waiting for a physics that doesn't yet exist to finally arrive at the right question. And somewhere in the asking of that question lies something larger than dark matter alone. Something about the relationship between knowledge and reality. Something about what it means to live inside a universe whose majority has been, and may remain, permanently beyond reach. There is a simulation running on computers distributed across dozens of research institutions around the world. It began in its earliest forms in the 1980s. It has grown progressively more ambitious, more computationally demanding, more physically detailed, consuming more processing time and more memory with each new generation, until it now ranks among the most complex numerical calculations that human civilization has ever attempted. It is called, in its most recent and powerful iteration, Illustris TNG, and what it simulates is the entire history of the universe. Not a metaphor, not a simplified model. A cosmological simulation that begins at a fraction of a second after the Big Bang, seeds the early universe with the slight quantum fluctuations observed in the cosmic microwave background, allows dark matter and ordinary matter to interact under the laws of gravity, hydrodynamics, thermodynamics, stellar physics, black hole dynamics, and magnetic fields, and then lets it all run forward in time for 13.8 billion years, producing a synthetic universe that can be compared, structure by structure, to the real one. The simulation works across an enormous range of scales, from the large-scale cosmic web of filaments and voids down to the internal structure of individual galaxies. The synthetic universe produced by Illustris TNG matches the observed universe with remarkable fidelity. Galaxy populations that resemble what Hubble and its successors have catalogued, cluster distributions that align with X-ray surveys, large-scale structure statistics that match the maps built from millions of spectroscopic redshifts. The success of these simulations is one of the most powerful validations of the standard cosmological model, and by extension of dark matter's role within it. But here is where the complication arrives, as it always does, dressed as a success story. When researchers run these simulations and look specifically for ultra-diffuse galaxies, objects with the properties of Dragonfly 44 and its relatives, they find them. The simulations produce dark matter-dominated, low-surface brightness, extended diffuse structures in galaxy cluster environments, and in roughly the right numbers. This was a triumph when it was first demonstrated. It seemed to suggest that the strange existence of ultra-diffuse galaxies was not an anomaly requiring new physics, but a natural outcome of known processes: dark matter halo formation, tidal stripping, feedback from stellar evolution, and supernova explosions disrupting star formation. Then the measurements got better. When the most precise observational estimates of Dragonfly 44's dark matter fraction were compared to the population of simulated analogs in Illustris TNG and similar codes, a tension emerged. The real galaxy appeared to be even more dark matter dominated than the simulated ones. The scatter in the simulations produced some extreme objects, but Dragonfly 44 sat near or beyond the edge of what even the most generous simulation predicted. Whether this discrepancy represents a genuine anomaly or a measurement uncertainty, the observational estimates of Dragonfly 44's dark matter content have been revised over the years, sometimes upward, sometimes downward, is still contested in the literature. But the tension, however quantitatively uncertain, points at something real. Because even if the simulations can produce objects vaguely like Dragonfly 44, the mechanisms by which they produce them are not fully understood. The simulations are not predictive from first principles in the way a physics equation is. They contain what are called subgrid prescriptions, recipes for processes happening below the resolution of the simulation, like the details of how a molecular cloud collapses into a star or how a supermassive black hole accretes and drives feedback. These prescriptions are calibrated against observations, not derived from fundamental theory. And this means that when a simulation produces something that looks like Dragonfly 44, it does so partly by construction, not entirely by prediction. The concordance is real, but it is not the same as understanding. The deeper complication, the one that neither the simulations nor the particle detectors nor the collider experiments have yet resolved, is that dark matter may not be a single thing. This sounds at first like a retreat, an admission that the original hypothesis was too simple. But it is actually something stranger and more interesting. Consider, ordinary matter, the 5% of the universe that we understand relatively well, is not a single substance. It is a zoo. Protons, neutrons, electrons, neutrinos, photons, a host of short-lived exotic particles, organized into atoms and molecules and plasma, and condensed matter phases of bewildering variety. The Standard Model contains 17 fundamental particles arranged into 3 generations of matter and 4 force carriers, and the full richness of chemistry and biology and geology and astrophysics emerges from their interactions. Why should dark matter be simpler? There is no theoretical reason that dark matter must be a single particle species with a single mass and a single interaction cross-section. It could be a sector, a dark sector, with its own internal structure, its own particle species, possibly its own forces that act only among dark matter particles and not between dark matter and ordinary matter. Dark atoms, dark chemistry, dark forces, a mirror universe of matter that parallels ours in complexity, but remains invisible to every instrument tuned to detect electromagnetic interactions, emerging into our perception only through the gravitational pull it exerts on the luminous structures it surrounds. If this is true, then the failure to detect dark matter through direct detection and collider experiments makes perfect sense. We have been searching for a single particle interacting through a known force. What we may actually be dealing with is an entire hidden sector of physics, as rich in structure as the Standard Model itself, coupled to our world only through gravity, the one force that everything shares and through which the dark sector's presence can be mapped, but whose details can never be fully resolved without a physics we do not yet possess. Dragonfly 44 takes on a new weight under this possibility. If it is composed of a dark sector, a complex, structured, self-interacting dark matter system, then what you are looking at when you look at that pale smear in the Coma cluster is not merely a galaxy with an unusual composition. You are looking at a structure built entirely from a parallel physics, a galaxy-sized object assembled from matter operating under rules we haven't written down, forces we haven't discovered, interactions we have never observed. A complete cosmic structure, ancient and stable and enormous, built from a physics that is not ours. And this is the point where the complications stop adding to each other and begin multiplying. Because if dark matter has internal structure, if it interacts with itself, then its distribution in the universe should not be smooth and featureless. It should clump, concentrate, form structures within structures. The dark matter halos around galaxies should not be simple spheres but complex, dynamic systems shaped by dark matter's own self-interactions. And at the centers of galaxies and clusters, where dark matter density reaches its highest values, these self-interactions could have dramatic consequences, heating the core, flattening what simulations of non-interacting dark matter predict should be steep density cusps, potentially driving observable differences in galaxy shapes and kinematics. Some observations suggest these differences are real. The so-called core cusp problem, the discrepancy between the steep central density profiles that collisionless dark matter simulations predict and the flatter cores often observed in real galaxies, has been a point of tension in cosmology for 2 decades. Self-interacting dark matter can resolve it. So, potentially, can baryonic feedback, the effect of supernovae and stellar winds pushing ordinary matter around in ways that drag dark matter with it. The debate is active, productive, and unresolved. What makes it especially pointed for Dragonfly 44 is this: a galaxy so thoroughly dominated by dark matter, so stripped of the ordinary matter that drives baryonic feedback, is an ideal test case for distinguishing between these explanations. If the shape of Dragonfly 44's dark matter halo differs from the predictions of collisionless simulations, and if that difference cannot be attributed to the feedback processes that are negligible in such a star-poor system, then the evidence for self-interacting dark matter becomes hard to dismiss. Dragonfly 44 is, in this sense, a laboratory that the universe built and placed in the Coma cluster for exactly the kind of experiment we need to run. The problem is that running that experiment requires measurements of Dragonfly 44's internal dynamics, the precise velocities of its stars, the shape of its halo, the density profile of its dark matter, at a precision we have not yet achieved. The galaxy is faint, distant, and sparsely populated with the tracer objects needed to map its kinematics in detail. The James Webb Space Telescope has begun to open new windows, but the full picture has not emerged. So we wait, as we have waited since 1933, as we have waited through every dark matter detector that came up empty, every accelerator run that found no new particles in the relevant range, every gamma-ray excess that refused to be definitively explained. We wait with better tools and deeper questions, and a problem that, far from simplifying as science advances, has revealed itself to be one of the most profound and stubbornly resistant mysteries in the history of human inquiry. And in the Coma cluster, 320 million light-years away, Dragonfly 44 simply persists. Ancient, dark, indifferent to our waiting, held together by something enormous and unnamed, drifting through a universe that made it and cannot explain it. Consider what it would mean to finally know, not the incremental knowing of a better measurement, a tighter exclusion limit, a simulation that matches one more observable. The real knowing. The moment, if such a moment ever comes, when a detector registers an unambiguous signal, when a theorist's equation clicks into place with the elegance that physics reserves for its deepest truths, when the particle or field or structural entity that constitutes dark matter reveals itself with enough clarity that the debate ends and the textbooks change and the universe becomes, in one decisive instant, a fundamentally different place than it was the day before. What would we learn? The question sounds almost naive, stated that simply, but its consequences ramify outward in every direction, into the nature of matter, the history of the cosmos, the future of the universe, and ultimately into what it means to be the kind of creature that asks questions about such things at all. Begin with the most immediate consequence. If dark matter is a particle, a WIMP, an axion, a sterile neutrino, something in a dark sector, then its discovery would complete the census of the universe's fundamental constituents in a way that the Standard Model's creation never achieved. The Standard Model describes the visible 5% with extraordinary precision. A dark matter discovery would hand us the blueprint of the remaining 27%, the dominant form of matter in the cosmos, the substance that built the cosmic web, that seeded galaxy formation, that made possible every star and planet and living thing. To know what dark matter is made of would be to understand, for the first time, the material reality of the majority of all matter that exists. Think about what that means in historical terms. The periodic table, completed over the course of the 19th century, revealed the building blocks of ordinary chemistry and unlocked the industrial and biological sciences that followed. The discovery of the electron, the proton, the neutron, and eventually the quarks inside them, gave us nuclear physics, quantum mechanics, semiconductor technology, and the entire architecture of the modern world. Each fundamental discovery about the nature of matter has cascaded outward into transformations of knowledge and capability that could not have been predicted at the moment of discovery. The discovery of dark matter's identity would be an event of that magnitude, or larger, because dark matter is not a component of the visible world that we had already intuited must exist, and simply hadn't isolated yet. It is something completely outside the framework of our existing physics, a substance that operates by rules we haven't written, that has been present since the first seconds of the universe, and that has shaped every structure in the cosmos without our knowing what it was. Its discovery would not extend existing physics. It would transcend it. But the consequences do not stop at fundamental physics. They extend in directions that are difficult to anticipate but impossible to ignore, into cosmology, astrophysics, and the deepest questions about the structure of time. The early universe, the period from the Big Bang to the formation of the first stars, roughly the first few 100 million years of cosmic history, is a regime where dark matter's behavior was decisive. The pattern of fluctuations in the cosmic microwave background, the oldest light we can observe, carries the imprint of dark matter's dynamics during that epoch. The distribution of galaxies across the sky, the statistics of the cosmic web, the abundance of galaxy clusters as a function of mass and redshift, all of these encode information about what dark matter was doing when the universe was young, dense, and hot. If we knew what dark matter was made of, if we knew its mass, its self-interaction cross-section, its coupling to ordinary matter, we could run the early universe forward from first principles with a precision currently impossible. We could test our models of structure formation against observation with the same rigor that particle physics tests the standard model at colliders. We could potentially resolve the tensions that currently exist between different measurements of cosmological parameters, the Hubble tension, the sigma-8 tension, tensions that hint at something incomplete in our model of cosmic evolution, and that might, just might, be pointing toward physics beyond standard cold dark matter. And then there is the question of the future. Dark energy, the mysterious component driving the accelerating expansion of the universe, accounting for 68% of its total energy content, is even less understood than dark matter. If dark matter's discovery opens a window into physics beyond the standard model, it is conceivable, though far from certain, that it illuminates the nature of dark energy as well. Some theoretical frameworks couple the two, a dark sector containing both dark matter particles and a dark energy field, linked by symmetries and interactions that would make no sense if either were considered in isolation. The discovery of one might cast light on the other in ways that current theory cannot predict because current theory lacks the pieces to see the connection. The future of the universe depends on dark energy. If it remains constant, if it is truly a cosmological constant, as Einstein originally proposed and as current data best supports, the universe will expand forever, growing ever colder and darker, with galaxies retreating beyond each other's horizons in a slow dispersal that will, in a time incomprehensibly far from now, leave every gravitationally bound structure isolated in an empty cooling void. The stars will exhaust their fuel, the black holes will evaporate, and what remains will be a near-uniform darkness, colder than anything we can currently measure, stretched across a space far larger than the universe we now inhabit. Dark matter halos, gravitationally bound, may be among the last coherent structures to persist, invisible archipelagos in an otherwise featureless void, holding the remnants of dead galaxies together long after the last light has gone out. Dragonfly 44 in this scenario is not a curiosity. It is a preview, a glimpse of what the far future universe will look like when ordinary matter has been exhausted and only the dark architecture remains. A prototype of the cosmos's final state, existing billions of years too early, built in a time of stellar abundance, but containing almost none of it. An object from the end of the universe's story, somehow present in its middle chapters. There is a biological dimension to this that is easy to overlook but difficult, once noticed, to set aside. Life, as far as we know, which is to say, in the only example we have, is built from ordinary matter, from carbon and hydrogen and oxygen and nitrogen and phosphorus and sulfur, organized by chemistry into structures of extraordinary complexity, from atoms that interact electromagnetically, that form covalent bonds, that dissolve in water, that catalyze reactions, that store and replicate and execute information in the intricate machinery of the cell. Life, in this sense, is a property of the 5%. It belongs to the luminous fraction of the universe, the thin film of ordinary matter that coats the gravitational scaffolding that dark matter built. But consider, life exists because dark matter was there first. Without the early concentration of dark matter into the first halos, ordinary matter would never have clumped densely enough to cool and collapse into stars. Without stars, there are no heavy elements, no carbon, no oxygen, no iron, no calcium. Without heavy elements, there is no rocky planet. Without a rocky planet with liquid water and a moderate temperature, there is no chemistry complex enough to sustain the process of evolution. Without evolution, there is no nervous system, no brain, no consciousness, no curiosity, no questions. You exist because dark matter built the scaffolding for your star. Your sun formed inside a dark matter halo. The galaxy that contains it was assembled around a dark matter core. The molecules in your body were forged in stellar interiors that could only form because dark matter provided the gravitational seeds for structure. In the most literal causal sense, dark matter made life possible. And you, the living product of that causal chain, the creature sitting at the end of 13.8 billion years of cosmic history, reading words about the universe that made you, are an indirect product of the substance you have never been able to identify. In Dragonfly 44, this relationship is present in pure, almost theatrical form. A structure built almost entirely from dark matter, with so little ordinary matter that complex chemistry is nearly impossible, with so few stars that planet formation is a vanishingly rare event, with no reasonable prospect for anything resembling life as we understand it. It is a galaxy in which the architect is present in overwhelming abundance, and the work it usually enables, stars, planets, molecules, cells, minds, is almost entirely absent. A galaxy of infrastructure without inhabitants, of scaffolding without a building. What it means to be alive, in a universe where the substance that made life possible is the one substance life cannot perceive. That is not a question science can answer alone. It is a question that science poses and leaves at the edge of its own domain, where the territory of physics ends and something else begins, something that might be called wonder, or terror, or both at once, which is perhaps the most honest response to the universe's genuine scale. There is a question that science does not ask, not because it is unimportant, but because it lives just outside science's formal borders, in the territory where measurement ends and meaning begins. It is not a question about particles or forces or the equations that govern the behavior of matter across cosmic scales. It is a question about us, about what kind of thing we are, given everything that Dragonfly 44 and the dark universe it represents implies about the nature of reality and our place within it. The question is this: what does it mean to be a knowing creature in a universe that is mostly unknowable? Not temporarily unknowable, in the sense of things we haven't gotten around to measuring yet. Not unknowable due to the limits of current technology, which history has repeatedly shown to be a temporary condition that ingenuity overcomes, but possibly, fundamentally, structurally unknowable, in the sense that the dominant component of physical reality may be something that no instrument built from ordinary matter and designed to detect electromagnetic radiation can ever directly perceive. What does it mean to be conscious in a cosmos whose majority substance is, by the physics of its nature, beyond the reach of the senses and instruments that consciousness has developed to understand its surroundings? This is not a counsel of despair. Science has made extraordinary progress on dark matter through entirely indirect means, and the history of physics is littered with examples of things that seemed permanently beyond reach. The interiors of atoms, the surface of neutron stars, the gravitational waves from merging black holes, that eventually yielded to cleverness and patience and the construction of instruments that previous generations could not have imagined. The future of dark matter research may hold surprises that render the current frustration retrospectively quaint, the way the pre-Rutherford assumption of an indivisible atom now reads as charming in its wrongness. But the structural possibility remains, and it is worth sitting with it for a moment, because it changes something subtle about the relationship between the human mind and the universe it inhabits. For most of recorded history, the unanswered questions of cosmology were unanswered because of scale and distance. The stars were too far to visit, too bright to examine directly, too ancient to have been observed from their beginnings. But the assumption was always that if you could somehow get close enough, if you could somehow build an instrument sensitive enough, you would see, you would perceive. The universe was, in principle, legible to a sufficiently capable observer equipped with sufficiently sophisticated tools. The cosmos was a text that could, in principle, be read. Dark matter introduces a different category of difficulty. It is not that dark matter is too distant or too ancient or too energetic. It is that dark matter does not, in any relevant sense, interact with the medium through which we perceive light, electromagnetism, the entire spectrum that our instruments were built to capture. The universe has a component that is systematically, constitutively invisible to the primary tool of astronomical observation. And this is not a quirk that better engineering can overcome. It is a property of physics. It is the way things are. What this means, and the weight of it accumulates slowly, the way large realizations tend to, is that the universe contains a domain of physical reality that may be permanently adjacent to ours, present everywhere, gravitationally coupled to everything we can see, and yet forever separated from direct observation by the basic structure of how matter and forces interact. Not a hidden dimension in the speculative sense of science fiction. Something stranger and more concrete. A sector of ordinary space-time, occupying the same space we occupy, shaped by gravity as we are, ancient and massive and real, and perceptually unreachable. Dragonfly 44 is the place where this unreachability is most visibly on display, a galaxy built from the unreachable, a structure whose dominant reality is something we can map only by its shadow on the luminous, an object that exists in the same universe as us, that has existed for billions of years, that is in every gravitational sense as real as the Milky Way or Andromeda, and that we know almost nothing about, not because we haven't looked hard enough, but because looking, in the conventional sense, may not be sufficient. And yet we found it. We found Dragonfly 44, not despite our limitations, but through our ingenuity within them. We built a telescope from camera lenses because the problem required an instrument that our assumptions had told us wasn't necessary. We measured the velocities of a handful of dim stars using instruments so sensitive they can detect a frequency shift smaller than the width of a single spectral line. We ran simulations of the entire universe on machines that didn't exist 20 years ago, producing synthetic cosmoses that matched the real one with a fidelity our predecessors could not have achieved. We mapped the distribution of dark matter across billions of light years using the gravitational distortion of background galaxy shapes, turning the invisibility of dark matter against itself, using gravity, the only force it cannot avoid, as the instrument of its own exposure. Every technique that has advanced our understanding of dark matter has been a form of indirect vision, a way of seeing something by looking at what it does rather than what it is, a way of knowing through consequence rather than observation. And this, when you think about it, is not so different from the way we know most of the things we know most deeply. We do not see the past directly. We read it in the light that traveled to us from ancient stars, in the isotopes preserved in ancient rocks, in the molecular sequences written into living cells. We do not see gravity waves directly. We measure the interference of laser beams in tunnels 4 kilometers long. We do not see the quantum field from which particles emerge. We infer it from the statistical patterns of scattering events at high energies. Indirect knowledge is not lesser knowledge. It is, in many ways, the most sophisticated kind, the kind that requires not just instruments but imagination, not just measurement but interpretation, not just data but the conceptual frameworks that make data meaningful. What Dragonfly 44 demands of us is an expansion of that imagination, a willingness to think about matter, about physics, about the nature of reality, in ways that do not begin with the assumption that the visible is the real. The universe has always been larger than our instruments. The history of science is the history of that gap narrowing, slowly, unevenly, with occasional leaps that seem, in retrospect, inevitable. Dark matter represents the current frontier of that gap, the place where the map ends and the territory continues unmarked. 320 million light-years away, in the gravitational metropolis of the Coma Cluster, Dragonfly 44 drifts. It has been drifting for billions of years. It was old before our solar system formed, before our sun ignited in the outer arm of the Milky Way, before the Earth cooled and the oceans pooled, and the first self-replicating molecules began the long, improbable experiment that eventually produced minds capable of looking outward and asking what was there. It was ancient when the dinosaurs walked the Earth. It was ancient before there was an Earth. And it will continue, presumably, long after the sun has exhausted its hydrogen and swollen into a red giant and collapsed into a white dwarf cooling toward invisibility. Because the dark matter that constitutes its body does not burn, does not collapse, does not exhaust itself. It simply gravitates, endlessly, patiently, indifferent to the timescales of stars and planets and the brief luminous experiments in biology and consciousness that those stars and planets occasionally enable. There is something humbling in this that goes beyond the usual humility that astronomy induces, the routine reminder of our smallness in space. This is a different kind of smallness, not the smallness of a body compared to a galaxy, the smallness of a knowing mind confronted with the boundary of its own knowing, the smallness of consciousness encountering the edge of what consciousness can reach. And yet, here we are, a species of primates on a rocky planet, orbiting an unremarkable star in the outer arm of an average spiral galaxy, in a universe that is 95% composed of substances we cannot directly perceive. And we found Dragonfly 44. We measured it. We weighed it. We understood, with extraordinary precision, what it contained and what it lacked and why that mattered. We built equations that described the invisible architecture holding it together. We ran simulations that reproduced its existence. We named the paradox at its center and have spent decades constructing the most sensitive instruments in human history to try to resolve it. We cannot see dark matter, but we know it is there, and we know what it does, and we know how much of the universe it constitutes, and we know that without it, nothing we call the cosmos would exist. That knowledge was assembled from nothing, from anomalous velocities and curved light and the statistical patterns of galaxy distributions, by minds that evolved to find food and avoid predators on an African savanna, and that turned out, against all reasonable expectation, to be capable of understanding the large-scale structure of space-time itself. Perhaps the deepest thing Dragonfly 44 teaches is not about dark matter at all. Perhaps it is about the relationship between ignorance and inquiry, about the fact that the universe does not owe us answers in the format we prefer, about the fact that reality is not organized around human perception, does not present itself in the wavelengths our eyes evolved to detect, does not confine its complexity to the scales our intuitions were built to navigate, and about the fact that despite all of this, despite every structural limitation, every technological constraint, every boundary between the luminous and the dark, the asking continues. The questions do not stop at the edge of the visible. They continue into the darkness, carried by something that may be the most improbable thing the universe has produced, a mind that refuses to accept the boundary between what it can see and what is real. Dragonfly 44 is there, enormous and dark and ancient, held together by something we cannot name. And we are here, still looking. That may be the most extraordinary fact in the entire universe.